Lesson 38, grounding. We will be able to describe grounding or earthing or what these terms mean. Let's go and look back to see where we've come from. We sort of started off with our new topic, electrical safety. What does electrical safety mean? And how can we keep ourselves safe with electricity? I've found a video that I'm going to show you guys during the week. And it's a really interesting video because it talks about what circuits used to be like back in Edwardian times, so 1910, so 1910 to 1905 to 1920, so 100 years ago. And essentially, we've come a long way with safety. It's very difficult to electrocute yourself in a modern home unless you really, really are trying to. We talked about power in the home last time. We talked about the switchboard being the place where all electricity comes into our house. The switchboard is also coupled with a meter to measure the amount of voltage you're using so you can get charged for your electricity. We said that everything is broken up into parallel circuits so you can switch things on and off. Each of these wires has three things that go into it. A active wire, sometimes known as the hot wire, because it's the wire that's got all the voltage. We've got a neutral wire, and we've got ground. And today our goal is going to be explain, what does this ground wire actually do? We talked about mains electricity. We said the electricity supply to our home is called mains electricity. It's an alternating supply. And we said that it changes every 1/50th of a second. It changes every 1/100th of a second, but takes 1/50th of a second to complete a full cycle from forward to backwards. Now, we said that direct current is reminding us that when it goes in one direction, whereas alternating current is when it goes one way, then the other way, then the other way, then the other way. It does it so quickly we don't even notice it. And there are some advantages to AC, and we're going to talk about what those are in a sec. And then we said that it makes a sinusoidal shape. And then again, I remind you guys, if you don't know what a sine wave looks like or a sine curve looks like, don't worry. You're not going to have to do the algebra. I'm just, at least not in trigonometry, at least not today, at least not in this subject. Maybe if you keep doing physics all the way down into, year 12, you will have to do some, but today, no trigonometry. Just showing you guys that this is what it looks like. This is when the current's going forwards, and this is what the current looks like when it's going backwards. And so it goes forwards and backwards. Now, let's talk about the voltage cycle just a little bit more. The period, and the symbol for period is T, of voltage is the time taken for one cycle or one complete wave cycle. So T in this case is the time it takes. See how here it's at 0, here it's at 0. Here it goes up, here it goes up. And that's how I know that I've completed one cycle, because it looks exactly the same. Now, if you get confused, you might think, oh, but there I'm at 0 at this point too. Yes, but here, instead of going up, you're going down. This actually represents halfway through the cycle. So T is one full cycle, up, down, and back. Up, down, and back. We've got another piece of information here. It's called the amplitude. The amplitude is how high. In this case, we also refer to that as V peak. What is the peak voltage? What is the maximum voltage you can get out of your circuit? So I keep saying that, there is a formula, by the way, that we can use to link this time it takes to complete one cycle to the frequency. Now, the frequency is actually a measure of, when we say frequency, we mean how many per a second. If I say, So if I want to know the frequency, I want to know how many times is this going up and down in 1 second. In this case, this is a very, very small amount of time. This is 0.02 seconds. So if I wanted to know how much will go in 1 second, I could take that 1 second, I could divide it by 0.02. That'll tell me how many times this will go up and down in that full second. This actually comes out to be 50. So it goes through 50 of these up and down cycles every second. Now, what we use is we actually use a symbol. We say 50 hertz. Just so you know, hertz means hertz is just a quick and easy way to say per a second. If I said, if I'm saying we're playing a musical instrument 400 hertz, that means that it'll go through a cycle 400 times in a second. If you are, if cars are going underneath a bridge at 2 hertz, that means that 2 cars are going under the bridge every second. It's just a way to measure things. So that's how we get to 50 hertz. And that's also how we can use this to backtrack to figure out what the, we can use this to backtrack to figure out, well, how quickly is it changing? What is the period? Now, this measurement of 50 hertz, the frequency, is different in different countries. Some countries have 60 hertz. Some countries might have only 30 hertz. So it's different in different countries, same as the voltage is different in different countries. Back in the day, it used to be different in the same state, in the same area, and that was really hard because what was difficult about that is something like an electric iron might work with your voltage, but if you drive down the street to your friend's house, it might not work there. So you've got to be careful, and then that might mean more voltages drops, which means it could get hotter. So you've got to be careful with those things. But that's what the voltage cycle looks like. Now, one last thing is this. I keep saying 230 volts. How do we get from 325 to 230 volts? So the peak voltage in this cycle to the right, whoops. The peak voltage in the cycle to the left is much larger than 230. It actually gets all the way out to 325. So we're not peaking at 230. So why do we call it? But it doesn't spend much time at 325. It spends a fraction of a second here. What we actually do is when we say, well, what we actually do is when we say, well, what is the average voltage? If I was to look at the average voltage, not including negative, just the average random voltage, how would I find that? You can find the average voltage from the peak voltage by doing this. You take your peak value and you divide it by √2, and that will take an average. And so the average to this is about 230. Of course, when I say average, I mean positive average. So what I mean is almost, I'm not sure if you're aware of the word modulus, but it's the positive version of this loop. Because ultimately, if we try to do the average of the whole circuit, it'd be 0, because plus and minus, we cancel each other out. Now, if I've got any smart asses in the chat that want to know why it's divided by √2, I tried to look it up, but I couldn't find an easy answer. And then I thought to myself, and then I tried to looked at a hard answer, and it still didn't really work. And then I thought, well, do I want to keep looking? And I thought to myself, you know what? No, I don't want to look. I can't be bothered. You guys don't need to know it anyway. If you want to look it up on your own, go nuts. But I can't tell you exactly why it's divided by √2, but that's the common way to get to the RMS, which stands for root mean square. If you want to look that up in your own time and tell me and make me look like an idiot later on why it's divided by √2, I would love one of you guys to tell me rather than me looking it up, but I just couldn't be bothered. So ultimately, when you take all this information, we can summarize it all here. In this picture, we've got the peak-to-peak voltage. So that would be from 325. That'd be from 325 to negative 325. Or 750 volts. So, yeah. The peak voltage is 325. The RMS voltage is 230. And so these are all the values that we would use. And so I guess when we talk about RMS, when we talk about 230 volts coming out of your power supply in your walls, that's because it's like an average. Yes, it does go between 325 and negative 325, but on average, it's about 230 volts. So that's how we sort of calculate these things. Now, why do we use AC in the first place? One advantage of AC is it's easier to convert to different voltages. You can think about that. It's going between 325 volts and 0 volts. What that means is that it's easier for example, you to power something like a massive TV, and a small nightlight can be powered off the same circuit, off the same type of wire. You just have to change the different currents and the different voltages. So that's one of the advantages of AC. In the electrical wires that go to your house, you're even jacking it up even higher. You've got tens of thousands of volts. But again, it's still going forwards and backwards. So you can use that to easily what we call transform, or sometimes we call this step down the voltage. It's easily changeable when it's AC. When it's DC, it's a bit harder, because when you want to drop voltage when you're using DC, you have to use voltage dividers, which is one of the reasons why I taught you that. But you know, that means you're kind of losing energy because you're dropping it over a resistor, whereas using it in this way is a bit better. So that's why we would use AC in the first place. Okay. You know what? I'm going to let you guys, what I'm going to do is this. I want you to read this, and I want you guys to answer, put an answer for this question in chat. Okay? I'm going to give you guys, I want you guys to work out an answer for this in chat. And then while you are doing that, actually, first I better make sure that I get the answer, just so that I don't, like you guys don't come back to me and say, sir, we did it straight away. Okay. All right, I'm going to eat as many noodles, as much noodles as I can, while you guys are trying to work out what the answer to this is. And then when you guys put an answer in chat, I'm going to stop eating noodles. So yeah, I'm going to see how you guys go. And go. Come on, guys. I want you guys, like, I'm having a great time. I'm eating my lunch, but I want you guys to tell me how much it's going to cost to run this circuit. That's what I want you to work out. I want you to write it in in the chat. Wait a sec, sir. Someone's got a question. Come on, guys. I'm gonna keep eating. All right. There are two answers here, but I think they're wrong. So we're going to do it together. I'm going to see how we go. Am I muted still? No, I'm not muted. Cool. All right. I almost finished my lunch. Just got a couple of spoonfuls left. So let's do this together. An air conditioner uses 8.7 amps, 230 volts. How much will it cost to run for 5 hours if it costs 31 cents to run at a kilowatt hour? Right. Power equals VIT. Look at that. V, but gotta be careful here because this will give us an answer in watts. Let's work out well, P equals VI, so but we're going to be careful because we want to know how much energy. So energy equals VIT. But let's do this one step at a time first. We've got 230 volts times 8.7. 230 times 8.7. 2001, which is equal to 2 kilowatts. Cool. That means that I've got E equals PT equals 2 kilowatt hours times 5 hours equals 10 kilowatt hours. That's 31 cents. So therefore 10 times, where is it? 10 times 0.31 equals $3.01. That's why I was sort of saying no to you guys. I was like trying to double check that I got that right. But yeah, Anthony got it. Yeah, Yvonne, you got it as well. It was you guys were saying. I think what happened is you guys may have been multiplying the 31 by 10, but you're going to remember that 31 is 0.31. Now, this is just a reminder on how to deal with kilowatt hours. This part of the chapter, for some reason, has a fair bit got to do with energy. And what they prefer to do is they prefer to teach kilowatt hours now rather than before. But I've already taught this to you guys. So all I'm doing is reminding you guys that these are the formulas. You already know these formulas. I've got you to practice them. And this is the conversion. You guys know this conversion, but I remember I'd prefer that you just calculate it. Also, by the way, we could even do this. 1 kilowatt hour equals 1.4 kilograms of CO2. So that means that we've released 14 kilograms of CO2 by using this air conditioner for 5 hours. So keep that in mind. That's just another nifty thing you can do. It's also a bit of a depressing thing, which is why I guess we're trying to find ways to be more energy efficient. By the way, if you want to go back to find out where I taught you guys this stuff, lesson 27. So just go back to that lesson. It is on YouTube if you want to check it out. If you type in year 11 physics lesson 27, you should be able to find it. Or you can just, scroll down the Compass page, the classroom page, and find it that way. Now, how much time have I got left? I've got 15 minutes left. So let's see how far we can get with grounding. In a PowerPoint, you have 3 sections. You've got a section in the top left, and we call that the live section. We've already talked about this. Australian mains power is at 230 volts. This means that it has the same effect as a 230 volt DC battery on devices like a lamp. So just treat it like a regular DC voltage. Don't really worry too much about it. Some devices have means of converting the DC voltage into AC voltage into DC voltage, but some devices just use the AC because they don't need to change it. One side of the AC, we've already talked about that. The terminal on the top left is called the live terminal. It's called the active terminal. This is the one that you got to be careful for, right? If you're gonna put a fork into a toast into a PowerPoint because you want to die, that top left one would kill you. The other two, not so much. Touching this terminal can be fatal. The other terminals carry 0 volts, right? The one on the top right, that's called your neutral wire. And the one on the bottom is your ground wire. So the neutral wire is like the other side of the circuit. So if one of them is positive, the neutral wire is your negative. It completes the circuit. Question? Or have I got someone that's accidentally unmuted? So that, cool. Okay. Now, the ground wire is a safety device. It's designed to keep you safe. Okay. It's designed to pretty much never get used, but sometimes it does come in handy when it saves your life. So let's talk about these bits and pieces. So let's talk about what does it mean when we say a ground wire. So this is the circuit for all this information we've done already. The only bits of news to you guys is these sections here. Let me show you a quick picture. I like this picture. So this is a picture of everything we've done so far. We've got here a main switch. So that switches on the power to the whole house, right? That goes through a meter box. The meter box calculates, how much electricity you've gone. And then that goes into a fuse box, or sometimes a switchboard. Switchboard is what we normally call it now. That can go through into your switch in your house. You've got 3 ports: the active port, the neutral port, and earth. Sometimes the neutral port and earth both go back to this neutral bar. That neutral bar is then connected to a stake. That stake goes straight into the ground. Now, when I say that stake goes into the ground, I actually want you to think, I'm not trying to make you guys think of these things like, oh, whatever, it goes straight into the ground. Obviously not literally. No, I mean literally. It goes into the ground. Grounding or earthing a wire is literally a wire that is placed into the ground. If you go to your meter box and you look underneath your meter box, underneath your electrical box, if you do this, you know what? If you do this, then you should be able to find a bar that goes into the ground, and that is your grounding wire. In power lines as well, you will also sometimes find a piece of white plastic that runs all the way down. I only recently learned that is the grounding wire for that electrical pole. I never knew that. So that is what's grounding your current. And so what does the grounding wire do? Why do we care about grounding? What's so good about earthing or grounding something? So electricity is, remember, ultimately when we break electricity down, it's just moving charge. Now, that means that you can create something which has got a lot of charge in it. Now, the ground or earth is so large that it cannot really take on a charge. So what it's really good for, it's a good place for dumping electrons or accepting electrons. If I've got a big piece of ground here and I've got a wire that goes down into the ground, let's just say in that wire I push a bunch of electrons. Electrons will happily go down into the ground. they're not going to get repelled because there are so many protons and so many electrons that they'll just go in there. And so in that way, this metal stake that's sticking straight into the ground outside of your house is actually the final part of the circuit. The earth, the ground that you are standing on, is actually the last part of the circuit, the last part of where electricity comes in. You know, the almost like the negative terminal of your house as a battery. Now, if there's a lot of places for electrons to go in, believe it or not, there's a lot of places for electrons to come out of. Electrons can also go back up into your house via the ground wire. So that's another way you can think about it as well, as, oh, that becomes a source of electrons. And remember, your current is going forwards and backwards because it's AC. So you're constantly pushing electrons into the ground and pulling them back out of the ground. So that's why it's good to have a grounding wire. Now you'll notice in this picture, both the well, you won't notice in this picture, but both neutral wires and the earth wires are connected to ground. That was based in this picture here. Both of them are connected to ground. So why do we need two wires connecting to ground? Well, the earthing wires are only used as a safety device in all power points and in most electronics. So what does this earthing device, what's so special about the earth wire that makes it a safety device compared to the other one? Well, let's jump in there. I'm going too fast, please stop me. Oh, this is another picture, by the way. So this is very similar to the one we used before, where it was like, okay, there's no earthing wires coming out of these light bulbs. They just go straight up to the neutral link, and then that goes straight out to ground, and that's how you ground your home. Sometimes there is a separate neutral wire. Sometimes this neutral wire actually goes back out to, you know, the street. So sometimes it'll complete the circuit that way, but not always. Sometimes it'll just go straight into the ground instead. Here we have a picture. In this one, we've got an earthing wire for every single light bulb, and this actually goes for every single socket, and that actually goes to earth before, rather than the other one, which goes to the neutral link, which then goes down to earth. So why is it good to have an earthing wire? What does this special, what does this green wire, what does this actually do to make things safer? Well, the most easy way that I think to think of what makes it safer is in an electrical device. Before we get to the electrical device, let's talk about the wires before they get to that electrical device. So a lot of electrical devices have three prongs. One prong is the active wire, or as we said, sometimes called the hot wire, or sometimes it's called the live wire. Doesn't matter, it's the deadly one, okay? That's the one that you want to avoid if you can. Whereas the blue wire is neutral. You can think of blue like a calming sort of, like, I don't know, but you sort of need to remember these colors. So blue is like the neutral wire. If you want to think about it, the brown one is, well, if you touch that one, you're pretty much in the shit. So that makes sense why it would be brown. The neutral wire is blue, whereas the earth is green and yet white. And it makes sense that the earth would be green because, yeah, you know, earth, grass is green, you know, makes sense. So these are the three wires as they're connecting to it. Usually, and these rules will change depending on the country that you're in. But for Australia, these are the colors of the wires. Blue is active, blue is neutral, brown is active, green and yellow is earth. You can grab a look at this, right? You can actually see the earthing wire is green and yellow. So yeah, it sort of works with our narrative, sort of makes sense. So how does the earthing wire work? Grab a look at this example here. Many devices that have metal exteriors or are dealing with water have a grounding wire. Sometimes as well, devices that have lots and lots of current have grounding wire. If the active or neutral wire breaks, the active or neutral wire breaks and touches the side of the metal core casing, then a person could complete the circuit to ground through themselves. So what you've got here is a toaster. This is a great example here. When this works, we've got this active wire gets connected by the switch. It goes through the element, heats up, and makes it really, really hot. And then it goes back out through the neutral wire, and then that goes back out to eventually that goes back out to ground. But at the moment, it just goes through the circuit, and that's it. And then bang, what do? You get yourself a nice piece of toast. Now, what happens if, let's just say you drop your toaster and one of these wires breaks? Instead of this wire connecting to neutral, it actually connects to the side of the metal frame. Now this whole metal frame is now electrified. Now, if you go and touch, and then remember, the electricity wants to get to ground. It wants to get back to the ground because the ground has got a lot of places where the charge can go. So if you come along and you put your hand, if you come along and you're standing here, and you put your hand on the toaster, what you do is you then provide a path for that electricity to go. That electricity can go through here, through the toaster, out in through this broken wire into the rest of the outer coating of the toaster, through your arm, through your body, and then it's into the ground. And now it's happy. It's happy because it's gotten to ground where it wanted to go. The bad news for you is it got to ground by going through your skin. And that might be very dangerous to you, especially if you've got a heart condition, because that could kill you. In fact, if you're standing in the wrong kind of way, that could just kill you if you don't have a heart condition. So what do we do in order to protect ourselves? What we do is we say this: there is the possibility that the electronics might break. And if they do, we put this earthing wire in. So now what happens is that the break happens, but instead of the electricity going all the way around the toaster, the electricity goes, hey, look at this. There is a shortcut to ground. There is a short circuit to get to the ground. I'm going to go into the grounding earth wire, and that's going to take me to the ground much faster than if I was to go to a person. And now a person can touch the toaster without getting electrocuted. Now, there are some other safety devices that we're going to talk about later on that sort of then tell the system, hey, there's something broken here. We need to fix this. But essentially, the grounding wire is a great sort of way to get around these problems. So I will quickly say, I'm going to quickly say this is the last little thing because the time's about to run out. The last thing I want to say is this. Yeah, I know it's 2:20. Don't worry, Andy. Last thing I'm going to say, this is not all circuits have 3 prongs, because not all circuits need a grounding wire. And I'm going to explain why later on. What I'm going to do for you guys is this. I'm going to set some homework for you guys to do over the weekend. I don't have time to do it now. The homework for you guys is going to be this. I want you to take a photo of the, if you can find it, a device with 3 prongs, a device with 2 prongs, and a device with and the core and the grounding stake, if you can find it at your house. That's going to be your homework. I'm going to put that on the classroom, and I'm going to remind you guys to do that after 3 o'clock, because I'm going to teach in the class myself. Sorry about the extra time, guys. Thank you. Have a good weekend, and I'll speak to you guys next week.
Bye, sir.
Yeah.
Bye, sir.
Bye.
Bye, sir.
See you.
Bye, sir.
Bye.